Introducing a new technology breakthrough that will change the way we run our lives forever. A completely new technology, developed and patented by Cavitation Energy Systems, should quickly replace energy creation as we know it. Among others, internal combustion systems, nuclear energy steam generators, and desalination generators will soon be outdated and replaced by cavitation technology. Not only will this proven and patented technology be available at a minute fraction of the cost of present technologies, it will release no greenhouse gases, or for that matter, any other pollutants whatsoever. This patented technology has been developed over the last 7 years by a dedicated group of scientists, engineers, and researchers in South Florida, and it's ready to be manufactured and released to the world. The following video explains the science behind the technology.
Our cavitation engine is the first commercially viable system capable of harnessing the power of cavitation to produce continuous steam energy without a boiler, at a fraction of the cost of using conventional, traditional steam methods. The applications of this new energy conversion system are very broad. The engine incorporates CES proprietary impact chamber design technology into a scalable steam generation system capable of producing superheated steam for significantly less energy than traditional boilers. Let me correct myself. Maybe we weren't the first to do this. Mother Nature actually was.
Far from being quiet, the ocean is filled with a cacophony of animal noise that can even disrupt the sonic transmissions of submarines. Most of the din is made by a surprisingly insignificant creature, the pistol shrimp. By snapping its claws, it can not only make communication sounds, but something far deadlier. These shrimps are its prey. It deals a knockout blow from a distance by using its claw as a sonic weapon. First, its claw is cocked like a pistol, then fired. The effect is literally stunning. As the claw snaps shut, it fires a blast of bubbles. Incredibly, as the bubbles collapse, they momentarily reach the temperature of the sun. This implosion causes a shock wave that stuns.
Our presentation today is going to be divided into two parts. Initially, we're going to review the science, engineering, physics behind why cavitation energy systems work the way they do. And then we are going to get into some of the very exciting applications of this technology. Prior to launching into a detailed technical discussion of why cavitation energy systems works the way it does, I think it's helpful to know where this is all going. What are the exciting applications? First and foremost, of course, is enhanced oil recovery, EOR, steam-assisted gravity drainage, SAGD, cyclic steam stimulation, and high-pressure cyclic steam stimulation. Then from there, we'll touch on power generation, conventional power generation using rotary expanders, and then the very interesting linear generator applications. From there, we'll touch on how this is important for textile manufacturing. Then we'll get into desalination and water treatment, which also includes the production water. This is the wastewater left over from oil recovery systems, ballast water treatment, and general wastewater treatment. Then we'll touch on marine propulsion, which deals with the interesting phenomena of salt water in our system. Basically, cavitation energy systems is really all about steam. Steam has been around for a long time. In fact, the whole industrial revolution was based on steam. And as we move forward, steam is still a very important working fluid. Not coincidentally, 90% of the world's power is still generated with steam, but most of that is using fossil fuels such as coal, oil, or natural gas. We are going to be talking about some of these applications moving forward, and let's take a look at how this actually works. Cavitation, the process of vaporization, bubble generation, and bubble implosion in a flowing liquid, is used as the underlying process within the cavitation engine. Modern diesel injectors are designed to enhance cavitation in the fuel being injected into combustion chambers. In the case of the cavitation engine, water is used instead of diesel fuel, and the injected water is filled with millions of cavitation bubbles. This injected water volume collides with the impact chamber wall at a very high velocity, in excess of 1,000 meters a second. Instantaneous pressures occur which crush the cavitation bubbles within the water droplets. Cavitation bubbles, as we've indicated, have the ability to focus intense energy and forces during their collapse. The resulting heat energy contributes to the continuous creation of superheat steam with the impact and expansion chambers. This slide shows the computational fluid dynamics simulation of an automotive injector output. As you can see, the output stream of the injector is saturated with millions of cavitation bubbles. These injectors are designed to produce lots of cavitation bubbles because it improves the combustion. As they expand, they disperse the fuel, and hence it burns better. In our case, we're impacting these cavitation bubbles on an impact chamber surface well before they expand beyond the point where they would normally be combusted. And this is essentially how the system works. This slide deals with the issue of the energy and the source of the energy in cavitation. Collapsing cavitation bubbles release enormous energy as predicted by the Rayleigh-Placet equation, as
Shown here is a differential equation.
for spherical bubble collapse and adiabatic conditions, meaning that there's essentially no heat loss as the bubble collapses. The typical temperatures have been estimated theoretically and observed to be between 4,000 and 8,000 degrees Kelvin. In the classic Brennan text, the mathematics and derivation of this are gone into extensively, and if you're interested in this, you can go ahead and pursue that text. You can find that on the Cavitation Energy Systems website. Unfortunately, maybe fortunately for us, but cavitation routinely damages machinery and is an unwanted side effect. You can see by the picture shown below what happens. This occurs typically in rotating machinery, impellers, propellers, turbine blades, and it's due in part to as these clouds of cavitation bubbles form around the blades and they collapse, there's an intense shock wave that occurs, and that shock wave can cause this scaling and erosion effect. Also, it's interesting to note, you may have heard of sonoluminescence, and this is the light pulses that are emitted by collapsing cavitation bubbles when water and other liquids are excited ultrasonically. This slide deals with the consequences of what happens when the gas bubbles in the expanding cloud of injector vapor collides with the surface geometry of the impact chamber. You can imagine this droplet of water, for example, saturated with expanding cavitation bubbles, suddenly hits the surface of the impact chamber. According to theory, the water hammer pressures that occur within that impacting bubble can exceed, due to the velocity, can exceed in excess of 50,000 psi. Now, the energy, or the thermal energy that's produced when these bubbles collapse, is a function of the ratio of the radius of the uncollapsed bubble divided by the radius of the collapsed bubble, which in this case can be very small, raised to the cubic power. And this can be quite substantial. As you notice in the diagram to the left, you get a lateral jetting, and after the bubble connects with the surface, and of course imagine this happening with tens of thousands of bubbles integrated over 7 jets from the injector. This slide demonstrates that thermolysis is what we believe is occurring within a collapsing cavitation bubble. By thermolysis, we mean the thermal separation of the oxygen and hydrogen atoms comprising the water molecule. You may be familiar with what happened at the Fukushima, Chernobyl, and 3 Mile Island disasters. They all involved hydrogen explosions, which occurred when temperatures exceeded 3,000 degrees centigrade as the reactors ran away. Temperatures above 3,000 degrees Kelvin or centigrade cause in excess of 50% molecular separation of water within a short time frame. Above 5,000 degrees, you get greater than 90%. As the gas cools, molecular hydrogen and oxygen reform. Under pressure, this mixture explodes, yielding water vapor, steam, which is vented from the impact chamber at high velocity as it passes through the pressure relief valve. Conductive and radiative heat energy are also released and captured. This slide shows a cross-section of a somewhat earlier version of the impact chamber design. What's important here is that you can see the orientation of the injector with respect to the impact chamber surface. These jets, 7 of them to be precise, the angle of that is such that it impacts the chamber at approximately 90 degrees, and it is about 400 thousandths of an inch away from the ejection orifice. You'll also note that we no longer have the pressure relief valve incorporated in the impact chamber, nor is there a thermocouple. But what's important here is the physical orientation of the fuel injector with respect to the impact chamber. This slide shows a detailed view of the impact chamber design. On the left, you'll see an exploded view. On the center slide, you see the impact chamber itself, the containment vessel, and the flange that holds it together. And on the right, you see a completely assembled system surrounded by ceramic insulation as well as foam insulation for stopping conductive heat loss. What's important here is the system is using 347 stainless steel, which has a very high emissivity to it, as well as being coated with black oxide. These parts haven't been coated with black oxide yet, but the whole point is to retain as much of the radiative component of the heat transfer as possible. So we capture the heat, the conductive heat, and the radiative heat, which is typically in terms of infrared. So that all in all, there's very little energy loss from the system.
What follows are the components of the impact chamber. The chamber itself is in the upper right-hand side of the image, along with the containment vessel below it. Next, we see the assembled impact chamber, followed by the impact chamber with the pressure relief valve installed. The entire system surrounded by insulation is there, and now we see it actually operating at approximately 1 injection per second. And you can see each of these injections, by the way, corresponds to 0.275 milliliters of water. And notice the extent of the shock wave and the power of this and how far it is from the impact chamber itself. We are increasing the pulse rate to 3 to 5 per second. In a practical system, this is where we would
normally operate. This is one element. Typically, in a 500 pound per hour steam system, you'd have 32 of these units ganged together and under central control by a computer. Here you see it in slow motion. It's like a gun going off, you know.
Mm-hmm. Reminds you of the shrimp.
This slide summarizes the energy measurements. What we have here is a breakdown of the individual energies used by the system components. The first one, of course, is the water pump. The second one is the hydraulic pump and accumulator. The third one is the heaters. And, of course, the fourth element are the electronics. We looked at the total power these required using these power meters, which you can see in the upper right-hand corner. And the output energy in terms of BTUs was calculated based on the fact that we were converting all of the water to steam, and each injection, of course, is 0.275 milliliters at about 5 per second. That over the time frame of the test gave us the total water and hence the total BTUs of output. We assumed between 1,000 and 1,100 BTUs per pound. Of course, that's at atmospheric pressure. In reality, as you can see from the output explosions, that the ability for this to perform work is probably more. But this was a very conservative measurement. We repeatedly made these tests and got essentially the same results. And you can see that it was about 5 to 1.
During our developmental work on the impact chamber, we thought it would be interesting to test injecting a solution of salt, a 4% solution of salt. I mean, this is not coincidental because the salinity of seawater is approximately 4%. Well, when we did this, we were shocked with the results, and you'll see that in the video that's coming up. We obtained these very dramatic explosions. So reflecting on this, we tried to conceive or postulate a mechanism for what exactly was happening. And within these collapsing cavitation bubbles, we have a plasma, a gaseous plasma, with a sea of surrounded by a sea of electrons. Now imagine that collapsing bubble with these large sodium ions around the periphery. A sodium ion typically has a redox potential of 1, meaning it needs 1 extra electron to become a stable metal. So in our hypothesis, the sodium ion picks up an electron, it becomes sodium metal. Everybody knows that when sodium metal reacts with water, as you can see by the reaction indicated over here on the right-hand side, that the byproducts of that reaction are sodium hydroxide, which actually, by the way, is a valuable industrial compound, and hydrogen gas. Well, hydrogen gas is stable under pressure unless it's under pressure in the presence of oxygen. So we've determined that there's oxygen in the impact chamber from the recombination during the cooling process of the oxygen molecule and the hydrogen, and it reacts and explodes. Now, what's especially interesting about this is because it suggests that we could use this seawater under these circumstances as a fuel. And you'll see in the subsequent video that the amount of energy that's released when this happens is fairly substantial. So this bodes potentially well in desalination applications as well as marine propulsion applications if we were to harness this energy through some type of expander apparatus and convert it to electrical energy or useful mechanical energy.
The following video of the saltwater injections is recorded at 1/8 speed slow motion. The explosions were so powerful that they damaged the pressure relief valve set to at least 600 psi after 6 explosions.
This is a 4-impact chamber segment of what ultimately will be used as a 32-impact chamber, 500 pound per hour segment. These, what you're seeing here, are piezo injectors. We'll be using hydraulic injectors for this.
What follows is an example of a 4-impact chamber unit driving a 20 horsepower V2 reciprocating steam engine, which in turn is operating through a power takeoff and a 12 kW generator. This is an example of the small scale power generation that the CES is capable of doing. During the following section, we're going to cover some of the more significant applications that CES is capable of. This would include enhanced oil recovery, power generation, textile manufacturing, desalination and water treatment, and marine propulsion. Enhanced oil recovery is perhaps one of the most important areas of application for CES. The term enhanced oil recovery, EOR, refers to the technology used to extract crude oil that cannot be extracted through conventional technologies from oil reservoirs. It is also termed as tertiary recovery process, as it takes place after the primary and secondary oil recoveries. Oil extracted via primary recovery accounts for 5 to 15% of the total reservoir, while secondary recovery can extract 20 to 60% of the total oil present in the reservoir. By installing enhanced oil recovery, 35 to 75% oil can easily be extracted from an oil reservoir. To extract the proved reserves, oil extraction companies are pushing the use of enhanced oil recovery in existing oil wells. Thermal enhanced oil recovery technology consumes hot water and steam to stimulate the extraction of crude oil from the reservoir. The commonly used steam injection enhanced oil recovery methods are cyclic steam stimulation, CSS, steam assisted gravity drainage, SAGD, and steam flooding. Steam dominates the thermal technology market and is significant in North America, as most of the imported crude from Canada, 35% of all U.S. imported crude, is extracted using SAGD. Per barrel energy costs in producing this oil are heavily dependent on the cost of manufacturing steam. We estimate the CES steam technology can cut the energy required for extraction by as much as 75%, making this oil more competitive in a market which has witnessed wide swings in crude unit prices. CES breakthrough technology will significantly change the various markets using steam because boiler efficiency is an important part of a purchase evaluation, since the annual cost of fuel can be easily 2 to 3 times the installed cost of the equipment. Therefore, a difference in efficiency and the resultant difference in fuel cost, which in the CES case can easily offset the difference of installing the product. In many cases, the fuel savings in the first year exceed the difference of the installed cost of the steam system. This slide shows an example of an advanced rotary expander manufactured by Vengeance Power. Banks of impact chamber arrays under central control can be combined to produce steam sufficient to operate this Vengeance Power or similar rotary expander turbine. This particular expander turbine will drive a 1.5 megawatt generator. This slide shows an example of a computer-generated model of a rotary expander driving a 1 megawatt generator. As you can see, a system like this in conjunction with our 500 pound per hour steam unit could easily fit in a 20-foot container and be brought to whatever location it was required. This slide depicts a linear generator. Linear generators have become very popular of late because they're very efficient, upwards of 90%. We will design such a linear generator using our impact chambers arrayed on either end to operate it under computer control. Linear generators are a very exciting technology, and we anticipate building a working linear generator with our CES system. The problem with linear generators is, of course, being able to detect the position of the piston so you know when to input a cushioning injection to keep the piston from crashing into the opposite side. This has always been the problem with these, cushioning and position control. but we expect at some point in time we can overcome this and have a working operational economic linear generator. Textile manufacturing is a major consumer of steam. It's used in all aspects of the process, obviously spinning, weaving, drying, heating, and maintaining the temperature of textiles. In our experience, much of the major textile manufacturing occurs outside the United States and Europe, and is done in countries where labor is less expensive, in particular India and China. In our experience, the largest textile manufacturing plant in India, located outside of Coimbatore, LS Mills, was very interested in this technology. It needed about 1,000 pounds per hour for their process. So this is an interesting application because in these large countries, particularly in Asia, there's a very, very considerable amount of textile manufacturing. Desalination is a significant market sector which is expected to reach upwards of $13 billion through 2016. It's estimated that 40% of the world's population lives within a short distance, 100 kilometers or so, of the coast. Many of these communities are in arid regions where fresh potable water is in short supply. In fact, only 3% of the world's water is fresh water, and 2/3 of that is located in isolated areas in glaciers or in the Arctic, or otherwise unavailable for human use. This is especially true in coastal regions of the Indian Ocean, Persian Gulf, and Southern Pacific, where not only fresh water is in short supply, but electricity and food resources. We envision the CES steam technology to be an important component in producing fresh water through desalination, more than likely in a trigeneration process where we're producing fresh water, we're producing electricity, and we're using the heat for absorption cooling. Produced water is typically a byproduct from some form of oil recovery process, either steam-assisted gravity drainage or more commonly in fracking. Oftentimes this water is highly contaminated with toxic compounds and needs to be detoxified. One of the ways to do this, of course, is through steam distillation or flash distillation. It's a significant market as the use of enhanced oil recoveries grow over the next few years. Ballast water treatment is a very significant market. With the tremendous expansion in global trade and container ships being a major means of commercial transport, ballast water is a significant issue, and the treatment of this water is very important. Ask anybody about zebra mussels in the Great Lakes and it gives you a pretty good idea of why you don't want to leave ballast water untreated, where this water has come from other countries, and then ships arrive at the United States and then dump this water into a U.S. port. So with this growth in the global transportation market, this is going to be a very significant component of it, and steam treatment methodologies, i.e. CES, will be very important in the coming years. The intriguing discovery that salt solutions similar to seawater can be made to explode following injection into the CES apparatus have potentially profound implications for the marine transportation industry. Besides being essentially an inexhaustible source of fuel, i.e. seawater, the other issue are emissions from ships. These remain one of the least regulated parts of our global transportation system. Bunker fuel, good old number 6, is the cheapest and most polluting fuel available and is used by most of the world's 90,000 ships. For example, in 1 year, a single large container ship, such as one of the Maersk fleet, can emit cancer and asthma-causing pollutants equivalent to that of 50 million cars. Bunker fuel contains up to 2,000 times the amount of sulfur compared to diesel fuel used in automobiles. And in fact, many ports, such as the Port of Long Beach, require ships to convert over to a less polluting diesel fuel before they're allowed to enter U.S. ports. In short, CES technology will eventually redefine marine propulsion system engineering using seawater as a fuel source, and we find that to be very exciting. CES technology is unique. No commercial inventions exist that functionally harness cavitation. CES is the only system capable of instantaneously producing steam on demand with significantly less energy than conventional heating. CES can produce steam at significantly less cost than conventional boiler-based methods. CES has comprehensive, strong patent protection covering all aspects of the technology. And our most recent patent, which we expect to be issued soon, has many claims, none of which have been challenged thus far. Cavitation is the only way to generate these temperatures, i.e. the 4,000 to 8,000 degrees C, short of LENR, low-energy nuclear reactions. CES is the only steam-based system which creates a usable source of energy through a mechanical process rather than internal or external combustion. CES uses just recently available modern technologies which are financially viable, i.e. hydraulic injectors, computer controllers, ultra-high pressure pumps, carbon fiber, and ceramics. CES impacts almost every aspect of modern living: power generation, transportation, desalination, heating, refrigeration, shipping, and so on.